Hey students, I thought a few of you might benefit by seeing some examples worked out, even before I get to, your questions on solutions. And so like I did yesterday, maybe I'll just add a little supplemental lecture. So we kind of finished up in class and the room's kind of occupied. So I thought I'd just sit here at my desk and say, okay, let's do just a few example ones. 1, 2, 3, 4. And I thought I would pick these 5. And so going to the end of chapter 12, let's just read these. The first one says, number 3, it says, to sterilize a 50-gram glass baby bottle, we must raise the temperature from 22 degrees Celsius to 95 degrees Celsius. So how much heat is required? So let me emphasize that there were 2 ways of calculating the energy. And this one with latent heat is if there's a change of state or a change of phase. And this one if there's just a change in temperature. And so it sounds like for this problem, it's simply just a change in temperature. So it would be the mass, which, let me hold off on writing down the mass because I'm kind of questioning what units to use. And I'll do that because it says it's glass. And so I'm going to grab the textbook here and put it in the screen and go back to table, I believe it's 1. Yeah, this is table 2. Here we go, table 1. And it gives the specific heat of various materials. And there it is, glass. And I guess we could do it in either joules or kilocalories. Why don't we go ahead and use joules? And so it says it's 840 joules per kilogram for each degree we warm it up. All right. So I'm going to put 840 joules per kilogram per each degree we warm it up. Now, that's important here because going back to the mass of the bottle, which they gave me in grams, I'm going to convert to kilograms so my units match. And that's what I needed to check. I needed to check if the table was listing this in terms of per gram or in per kilogram. It looks like it's per kilogram. And I think I remember that now from the lecture, commenting on that. Okay, now the change in temperature, I guess, would be 95 minus 22, because we're going to go up to 95, and that would be degrees Celsius. I might point out that a change in temperature on Celsius and a change in temperature on Kelvin are one and the same. So any formula where we have change in temperature, we could use either Kelvin or Celsius, because as we talked about, the size of a division is the same. There's still 100 of them between ice water and boiling water. So whether it's a change in Kelvin or a change in Celsius is kind of irrelevant. Now, Fahrenheit, they're a different size. So that's a different story altogether. But that's why many of our formulas that say change in temperature, we never specify Celsius or Kelvin. It's just whatever we have to work with. All right, so 0.05 for the mass, 840 for the specific heat, and 95 minus 22. I guess I could do that in my head. That's not a big one. But coming out to be 3,000. And it looks like 66, but I'm going to just follow 2 significant figures, which is always kind of leery. Is, that one significant? Yes, got to be between 2 numbers. That one, maybe not. Maybe we should put a line under it, or maybe we should just go to scientific notation, and then there's no doubt. All right. So that's probably the easiest one here. All right, let me scroll through the book here and get to number 12, and let's read that. So number 12 says, a bag containing 0 degrees ice is much more effective at absorbing energy than one containing the same amount of 0 degree water. Okay. Now, that's just a statement, and we should probably talk about that. But I guess what I'm getting at is if you already had it in the form of water, and then you warm it up, say, 10 degrees, you would calculate this is the energy it took to warm it up. But if it starts off as a bag of ice, it's still at 0 degrees though, the first bit of energy would be calculated here, and now you would just have water at 0 degrees. So then you got to warm that up. So it would be the sum of those two. You would have a phase change and a warming up. And that's kind of what this problem is getting at. A says, how much heat transfer is necessary to raise the temperature of a 0.800 kilogram of water from 0 to 30 degrees? Okay, so A is just a change in temperature. There is no change in phase. Let me just double check that. How much heat transfer is necessary to raise it from, water of 0 degrees to water of 30 degrees? So we just need to look up the MC delta T. So the M is given as 0.8 kilograms. The specific heat is the 4,186 joules per kilogram per each degree. And it looks like we're going to warm it up 30 degrees if it goes 0 to 30. So this would be the answer to, I guess, the first part, A. So 0.8 times 4,186 times a 30. And so looks like about 100,000. And so 100,464 joules. Maybe to three significant figures, I should just write it as 1.00 times 10 to the 5 joules. Okay, but then it says how much heat transfer is required to first melt it. Okay, so this goes back to number 3, where I was saying this is the Q equals ML, and in this case, F. It's fusion. Now, it's 0.800 kilogram. That's how many kilograms we have. But we need to go to table 2. Here it is. And look up water. And it is 334 kilojoules per kilogram. So this would be 334 kilojoules. So thousands of joules per kilogram. So that the kilogram cancels off. And so 0.8 times 33423. Making 2.67 times 10 to the, I believe that would be a 5. 1, 2, 3, 4, 5 joules. And so notice how much more energy it is to just melt the ice compared to warming it up. I mean, it would be 2 times, 2 2/3 times more to melt the ice than to just warm it up. And that's not even counting warming it up. Let me check with B here. B says, how much energy is required to first melt it and then raise its temperature? Okay. So let me add to that the 1.00 times 10 to the 5, now that we have to also warm it up. So there would be 3.67 times 10 to the 5 joules total. The first 2.67 is to melt the ice or break the bonds, and then the other part is to warm it up. And so that is a lot more energy than that. And then, of course, C says, explain how your answer supports the contention that the ice is more effective. So, in other words, just takes more energy. Just downright takes more energy. That's what they're trying to say there. All right, well, if that was helpful, Let me try number 30. And 30 says, oh, hang on here. Looks like I need a pause for a second. All right, finally back here. Okay, so let's continue on here. So we were working on number 30. Number 30 says, calculate the rate at which heat conducts through a house wall that are 13 centimeters thick and have an average thermal conductivity twice that of glass wool. So this is that fiberglass. Assume here that there are no windows and no doors. So obviously windows and doors are thinner, different material. You can take the surface area to be 120 square meters and their inside surface to be at 18 degrees Celsius while the outside is 5 degrees, so on the cold side. And so this is saying that if we take our little formula for thermal conduction, we said it depended on the material, the area, the temperature difference, and the length at which it is conducting through. And so we're going to get this rate, energy per time. And maybe the first thing I'll do is I'll look up the thermal conductivity of our material. Now it doesn't, what does it say? That the average thermal conductivity is twice that of glass wool. Okay, so they're not saying it's glass wool, but at least they are having us look to that. Where is our glass wool? Here we go. And so it gives a number here of 0.042. And let me just read it again. Did they say double calculate the thickness? And has an average thermal conductivity twice that. So if we're trying to keep our house warm inside, the fact that it's twice that is not so good, but it's still a pretty small number, 0.084. So I will put 0.084. And I will notice the units are joules per second. Then multiplied by a meter and multiplied by degree Celsius. Okay. They don't really show it quite well, but they mean this, that the whole quantity of this is downstairs. In fact, it might look better if I write it as joule over second, also over a meter, also over a degree Celsius. So then when I put in the other things, like the size of the wall, 120 square meters, and the D is the distance that the heat flows, so it's not like the height of the wall or the width of the door wall, but it's the thickness of the wall. That's where it's going to flow. It's going to flow from the hot, or I should say warm room of 18 degrees C, and it's going to go out to the outside surface. And so somewhere in there they said it was 13 centimeters thick. Where did it go? Oh yeah, right at the beginning there. It says conduct through the house walls that are 13 centimeters thick. And of course, now you can see how the 2 meters downstairs will cancel with that one. And then also there's a temperature difference. And so I'll go 18 minus 5. And that would be in degrees Celsius, which change in temperature on Celsius and Kelvin, as I just mentioned, are the same. And of course, you're going to end up with an answer that is at a rate of so many joules per second are leaving the warm room and going out to the cold environment. And of course, that's without any windows or doors or somebody opening a door or a loosely fitting window, whatnot. All right, so I got distance, I got area, I got temperature difference, and then I got the thermal conductivity. So 0.084 goes here, times 120 here, times, looks like a 13-degree different, divided by fairly small distance. It's just the thickness of a wall, about a normal number for a wall. But it's about 1,008 joules per second. And I guess to three significant figures, it would be 1.01 times 10 to the 3 watts. So that's the heat that's leaving the room. So then B goes on to say how many 1 kilowatt room heaters would need to balance the heat transfer. All right, so again, if this much is coming out, which is about 1,000 watts, this is pretty darn close to 1 kilowatt. And that's how much is flowing out of this room. And the room would start to lose its temperature if you don't keep that up. And so we've got to put this much into the room. And so maybe we've got to be burning natural gas or running an electric heater, but we'd have to put it in at this same rate. So we need, 1 kilowatt worth of power. And so what they say is, how many 1 kilowatt room heaters would you need? Well, I guess it's just one. And so we would need 1 kilowatt in the room, because that will then keep the temperature the same, because this would be supplying energy at the same rate it's being conducted out. All right. Well, I'll move on to another one. Number 51 is kind of next on my list of helpful example calculations. 51, I can't seem to nail it down. The Hawaiian volcano. The Kiowa... I wonder how you say that. Kailua volcano in Hawaii is the world's most active. Whoa. Escorting about 5 times 10 to... 5 times 10 to the 5 cubic meters of lava, which is at 1,200 degrees Celsius each day. What is the rate of heat transfer out of the earth by convection if this lava has a density of 2,300 and it eventually cools down to 30 degrees Celsius? You can assume that the specific heat for lava is the same as that for granite. Okay, so when they talk about the amount of energy, this is the calculation. We're going to actually change temperature. I suppose a case can be made where there's a phase transition, because somewhere in here, I guess it would have to go from a liquid into a solid. And I don't think that's what they were after in this. I suppose I could look at the latent heats and see if they have anything listing like a basalt rock, Plumbus rock, and I don't see anything. We can look at its temperature. So I don't think we need to worry too much about the phase transition. It's really just a cooling down. And so could be better stated. But the other thing I will do is remind you that density is mass over volume, which of course means mass is density times volume. So if we put those two together, we could say, if you take the density of the lava and multiply by its volume, you would get mass. Then if you took the specific heat and the change in temperature, you would be getting how much energy comes out here. And if this is a rate, I think that's what they said, assume the specific heat cools is like granite. What does it say? What is the rate of heat transfer? So I will divide both sides by time, and it looks like we would have density times volume per time times the specific heat times delta T. And so I'm going to group that together because that is the volume per time. And that's what it says. At what rate is heat transferred out of the earth by convection if the lava has a density of... So they're giving me the density. Wait. If the lava has a density of, where's the rate? Oh, per day. There it is. It is 5 times 10 to the 5 cubic meters per day. Okay. So I'm going to go ahead and put in the density. So this is the 2,700 kilograms per cubic meter. And I'll put in the volume per time. This is 5 times 10 to the 5th cubic meters per day. This is the specific heat where they said you can go ahead and assume that the specific heat of lava is about the same as granite. All right, let me come back over here to the specific heats and look for... Go ahead and assume that the specific heat for lava... Oh, they put it right here, under concrete and granite, and I guess in this case maybe a basalt since it's a lava. Okay, so this is 840. So 840 joules. Let me just check the units. I believe that's per kilogram. Yep, joules per kilogram per each degree. And the cooling down, if you will, is 1,200 minus 30. And that would be in degrees Celsius. So degrees Celsius would cancel off. And if you look here, cubic meters would cancel, so this would be kilograms per day. So that would cancel off kilograms, and it looks like we would have the unit of joules per day. How much per each day? And the question says, what is the heat transferred out of the earth by convection if, okay. And this is, again, per day. Usually when we give an energy transfer, it's per second, so it's watts. So I have a feeling I should keep going with this answer, but I'll pause here for just a moment as I put in my numbers. So 2,700 times 5 times 10 to the 5 times 840 times 1,200 minus 30. And so this would be 1.3 1.33 times 10 to the 15 joules, 1.33 times 10 to the 15 joules in one day. But continuing on, if I wanted to put this in per second, so 1.33 times 10 to the 15 joules per day. Let me then say, if I want to get rid of days, I can convert it to, say, hours, because there's 24 hours in a day. So that's just one, because we have this number on top is equal to number on bottom. But of course, what it does is change it then to joules per hour. And then if we want to get it in seconds, we can say there's 3,600 seconds in 1 hour. That way, and hours would cancel off, and it's going to be per second. So we are going to get joules per second. And a joule per second is a watt. All right, so I'm going to take this number and now divide it by 24. Now divide it by 3,600, and it looks like 1.53, let's call it 6, times 10 to the third, or 10 to the 10th watts, which it might be kind of nice to write as times 10 and times 10 to the 9th. Because that right here would be a gigawatt. And that times 10 is 15 point, and I'll just do 3 significant figures. So 15.4 gigawatts. Okay. I'm not sure that adds up right. Man, look at that. Okay. And so this would be 1. Let me just hit enter again. Divided by 24, divided by 3,600. No? Yeah. Okay. Yeah. Okay. I guess that's fine. I don't know why I freaked out about that one, but it just didn't seem quite right. I guess because, let me look at your author here. I thought your author had a much bigger number. I see. Your author did it in mega. So this would be 15,400, changing a billion to a million. So I'll make that 3 decimals bigger. Yeah, okay. And that would be about a 1.45 times 10 to the 4th megawatts. Yeah, and then your author says 2 times 10 to the 4th. I don't know why he only did one significant figure, but anyways, he's in megawatts and I'm in gigawatts. But yeah, 15.4 gigawatts. So a lot of energy coming out of the center of the Earth, as you could imagine, and that's not the only place heat is coming out, but fortunately the heat is coming out. Otherwise, it will build up and make giant earthquakes. Probably having that too. But at the moment, we're not having any earthquakes. So kind of happy with that. All right, and the next one on my list was the 58, which says, what? Let me find 58 here in your book. Where is it? Here we go. It says, calculate the rate at which heat is transferred by radiation from a car radiator at 110 degrees Celsius into a 50 degrees Celsius environment. So this is the radiation. So this is Stefan's constant times the emissivity, the area, and the temperature to the fourth. And we've got the object, and then what I called in class the room, because it was the room, but I suppose maybe I should put, for this one, environment, because we would be losing energy to the environment, but also gaining from the environment. And so it's the difference between those is Stefan's law. Oh, hang on, I got somebody else here coming in the office. I'm going to pause and be right back. All right, so I'm back. Let's continue on here. And, of course, this first one is just Stefan's constant. So 5.67 times 10 to the negative 8. Let's take a moment here and go through our book here. And let's see, we got conduction, convection. So here's the section on radiation. Here's the Stefan's constant, Stefan Boltzmann's constant, 5.67 times 10 to the minus 8. Yeah, okay. And then we've got the joules per second. We've then got the square meter. And then we've got Kelvin to the fourth power. And again, it's the whole thing is over that. Okay. So there's the Stefan's constant. Now here, I think I need to keep reading in the problem here, because we need to know how well this radiates. It says if the radiator has an emissivity, boy, that's a hard word to say, emissivity of 0.75. So that's the E. So 75% of the energy gets emitted, or put another way, the surface is made out of something that reflects back 25%. So maybe it's kind of a polished surface, but not real polished, or maybe it's an unpolished metal, maybe even painted a dark color. Actually, that sounds like a good number, that if the radiator was made out of brass, or maybe a little stronger, out of bronze, it would work. Okay, but anyways, emissivity of it. And then the area is 1.2 meters squared. And then I would have this last term, which, let me just go t to the fourth minus t to the fourth for a moment, and I'll worry about putting those numbers in. But I'll work with what I have so far, which of course square meters would cancel off, and we're going to be left with joules per second and Kelvin to the fourth, and then we will have this temperature difference. And of course, here's what I wanted to point out. It's in Kelvin, so I need to put the temperature in Kelvin. And then, of course, the number, well, let me just get a number here to work with. 5.67 times 10 to the negative 8. And then the 75%, and then the area. So 5.103 times 10 to the minus 8. And then I can put in the temperature of the object to the fourth power. Now, they say this radiator has warmed up to 110 degrees Celsius. So adding 273 makes 383 Kelvin to the fourth power. Okay. And even then, it's trying to pass it off to a pretty warm environment. So maybe this is driving the car in the desert here, because this is still 323 Kelvin to a fourth power. Okay. And keeping that in mind, then I'll see what do I get. So 383 raised to a power of 4 minus 323 raised to a power of 4 inner. So that's the difference between those. And then times 5.10 times 10 to the negative 8. So this radiator would be radiating 542, and again, this would be watts, because the Kelvin to the fourth would cancel off, and we would have joules per second. So not much, although you could probably feel it. This was what I was talking about in the lecture, that if you've ever stood near a car after it's been driven, you can kind of feel that warmth. You put your hands in front of it, you can feel that energy. They're at a wavelength that I was saying it's kind of hard to describe because you couldn't see it with your eyes. But it's still giving that off, and we could have special instruments that could measure it, or special cameras that could take a picture and then convert that into what we call false color, a color that our human eyes can see, so we'd have some idea how warm things are. And so these are those infrared pictures, like the one I was showing you in the lecture with the house, and it had the reds and the greens and the blues kind of showing the different temperatures of it. Okay. So again, this is what's coming from it. Now, the other part of this is kind of an important engineering question anyways. I don't know too much about the life science need for this, but it says, is this a significant fraction of the heat transferred by an automobile engine? And to answer this, go ahead and assume that the horsepower is about 200 horses, which they say is about 1.5 kilowatts, which I'm going to write as 1,500 watts. And then they say most automobiles are kind of operating in that range of 25% efficiency. In other words, what they're saying here is you burn a lot of fuel. So I'll say the power in the fuel. Then they're saying with an efficiency of 25%, that's how much power goes to a kinetic motion, which I will now put at 2,500 watts. And so I would argue that by that statement of efficiency, divide by 0.25, that's the same as multiplying by 4. So that would be 60. So we're burning enough fuel to be 6,000 watts. And so I'll go 6,000. And of course, as they're saying, 1,500 of it goes actually to the kinetic motion of the car. But that also means another 4,500 watts is what we call waste heat. The whole process of burning the fuel, making the heat, we basically make more heat than results into moving the car. And that's what the 25% efficiency would say. It would say then 3 times this amount right here, so 3 times the 1,500, the 4,500, is actually going in to heat. And so the engine needs to get rid of that heat. And so the engineers need to design a way to get this much out, and that would be 4,500 joules every second. And this part here, back in first calculation A, says maybe 500 would just kind of come out just because of radiation itself. You just have a hot radiator and it radiates it away. But even if we subtract this 500, and it is a hair over 500, we still would have a hair under, I'll say less than about 4,000 joules every second, that we still have to get the heat out. So this is not even close. And I think that's what they're trying to say. Let me kind of flip down to the answer. What does the answer say? It says... Can I find it here? It just says it is not a significant fraction because the heat is primarily transferred by other means. Yeah, so that, we need other means. And of course, that's why we actually have then a water pump. And so you circulate water around there and then blow the air through the radiator. Or if you're driving, you don't have to blow it through. But a car that's kind of idling, you'll hear the fan kick on and then blow the air through the fan to try to get energy out in a conduction/convection way instead of just by radiation. In fact, if I understand right, it's about a 50-50 that half of it, so I'll call it the 2,000, come out by circulating the hot water through the radiator and blowing the air over the fan. And the other 2,000 is the fact that the burnt gases, what you would call the exhaust, carries with it a lot of heat energy also. And so just letting that exhaust gas out lets out that waste heat. It, of course, also lets out the burnt gasoline. That's the biggest reason is, we already burnt that gasoline. We can't use it again. So we let it out the tailpipe and then we burn more gasoline. All right, but getting a little bit more into the engineering, but it's kind of a fun question. All right, so I hope these quick little examples helped and would be a supplement to your lecture.